Bismillahirrahmanirrahim. Alhamdulillah, thanks for Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Alhamdulillah. Thanks for Allah subhanahu wa ta'ala who has given us one more day, one more chance to repent to Allah subhanahu wa ta'ala. Imagine how many people slept last night but could not wake up. So this is the sole mercy of Allah subhanahu wa ta'ala that he has given us yet another chance to repent to Allah subhanahu wa ta'ala. How to repent to Allah subhanahu wa ta'ala? By thanking whatever he has given to us, whatever he has bestowed upon us. Alhamdulillah. Whenever you get there, try to mute your microphone. This should be the very first thing. All right, if you look into the highlights of the previous lecture, we got an idea. Foundation is there about another type of differential equations known as partial differential equations. Our difference between ordinary and partial differential equations is pretty much based upon the difference between ordinary and partial derivative. So we need to see the function of variables, how many independent variables are there. If there is only one, so we will move on to talk about ordinary differential equations eventually. And if the function depends upon more than one independent variables, so we need to talk about partial differential equations. Remember, in both cases, we talk about one dependent variable. Chances are there we could have more than one dependent variables. But in this case, there will be a system of differential equations. Generally, when we talk about single differential equation, we will be having one dependent and one or more than one independent variables. Generalized representation is there. What sort of elements should be there in order to describe a partial differential equation? We see that there should be independent variables like x, y, z, or t as a symbolic representation. There should be a dependent variable u and its partial derivatives with respect to those independent variables like x, like y, like z, like t. So up to what depends upon the order of the differential equation. For example, if you cut it down up to over here, so it is going to be second order, same is the case, but involving third order partial derivative, the equation is going to be third order. So we see that things go on. So we need to take a suitable combination of those dependent, independent, and derivatives. Depends upon this scenario. So we say that this is going to be a relation between them, a relation of the dependent, independent variable and their derivatives of the dependent variable with respect to those independent variables. So like in this case, you see that what are there? We have x, we have y, independent variables. So we have u, dependent variable, its partial derivative with respect to x and y. So those 5 elements are there. 2 independent variables, 1 dependent, and 2 partial derivatives. You see that second order derivative is there, so it is going to be second order differential equation. Order and degree, we have gone through with that. Pretty much the same idea as we talk about ordinary differential equations. Linear and non-linear. So the very first characteristic is identical. Secondly, the coefficients of the dependent and its derivatives are functions only of the independent variable. So this is going to be the restriction. Based upon these two properties, characteristics, we distinguish between linear and non-linear partial differential equations. Homogeneous, non-homogeneous is a slightly different idea in comparison of ordinary differential equations. We say that a partial differential equation is said to be homogeneous if each term in the equation contains either the dependent variable or one of its derivatives. So if a term is free from either dependent variable or one of its derivative, we say that it is going to be non-linear. As an example, non-homogeneous. As an example, this one does involve derivative independent of dependent variable as well as of any of its derivatives. So we say that that one is going to be non-homogeneous. Yes, if there is 0, for example, to the right hand side, so then we will regard it as homogeneous. General and particular solution, yes. No, since we are talking about function of more than one variables, so instead of talking about arbitrary constants, we need to talk about sometime arbitrary functions. And the one obtained from the general solution by giving particular values to arbitrary constants or arbitrary functions is going to a particular solution. For example, this one is going to be a general solution of that particular differential equation. How many arbitrary functions are there? As many as the order of the differential equation is there. So f and g, they are arbitrary independent functions. So this is how we say that this expression or relation is going to be general solution of that partial differential equation. However, if you take particular expressions for f and g, plug in over here, it will turn out to be particular solution independent of arbitrary constants or arbitrary functions. Conditions are there because now we are talking about partial differential equations. So generally, ordinary differential equations are associated with initial conditions. So this is how we will be having initial value problems. And generally, partial differential equations are associated with boundary conditions. And we say that the problem is going to be boundary value problem. Why do we need of conditions over there? Because we see that, yes, all of them, u being a function of xy, function of xy, function of xy, function of xy, they're all going to satisfy this second order differential equation identically or simultaneously, not only the value but also its second derivative with respect to x and y. So we have to accept them as the solution. So we are forced to accept them as the solution of this partial differential equation. So how many solutions are there? Infinitely many. To restrict to one or unique solution, there should be certain conditions. What are the conditions that could be imposed? Either the boundary or initial conditions are there. Boundary conditions when we talk about partial differential equation, because now we move on. Just like if you remember from calculus, we have a single variable. It means that we are talking about a line, combination of two variables. It will turn out to be plane. 3, it will turn out to be space, and this is all. And at least 2 of them are this. So it is not going to be a line, of course. It is going to be at least a plane over there. So region is going to be a plane at least, or could also be a surface in 3-dimensional space. So this is how we will be having more than one conditions. Remember, boundary conditions are always going to be more than one. Initial conditions could be one. One single condition is there. Boundary condition can't be one. Because of boundary, there should be a boundary. Directly conditions, very simple idea is there. If the conditions are free from derivatives, then the conditions are known as directly Neumann conditions involving derivatives. So free from derivatives, directly involving derivatives, Neumann, and the combination of them is going to mixed or Robinson or radiation conditions involving u and its partial derivative. I mean, in other words, combination of first and second. First one, free from derivative. Second one, if there is one condition, it is going to be in terms of derivative. So combination of them is going to take us to mixed or Robinson conditions. How do we form a partial differential equation? Sometime we can get rid of arbitrary constant by eliminating arbitrary constants. We can form a partial differential equation. Assume that we have a relation between dependent variable u, independent variables x and y, and two arbitrary constants a and b. For example, whatever the expression is there, it's a generalized representation, f of x, y, u, a, b. So it is going to be a relation between them. They are going to relate. They are going to be related with each other. So we have a sort of relation between them. We get to talk about generalized or the particular expression from the generalized representation. Now, what is the criterion behind the scene to get rid of those arbitrary constants? There are basically three cases. Number one, if the number of arbitrary constants is equal to the number of independent variables, as we see in this case, two arbitrary constants, they are equal to two independent variables. So number of arbitrary constants, they are equal to arbitrary independent variables. So this is the first case. How do we get rid of those arbitrary constants a and b? So we basically partially differentiate the given relation, the relation between dependent and independent variables along with the arbitrary constants. And this is all playing around with some simple algebraic operations being implemented. So we get rid of those arbitrary constants. So this is the criterion. We need to differentiate them. Take a particular case, u is going to be an expression involving x and y, two independent, two arbitrary constants a and b. So the criterion states that we need to partially differentiate with respect to x and y. So this is of a is a, b is a. So plug in those values over here. So this is going to be corresponding partial differential equation. So how do we form this one? By eliminating arbitrary constants. If the number of arbitrary constants equal to the number of independent variables in this case. Secondly, if the number of arbitrary constants are less than the number of independent variables. So normally we can have more than one partial differential equations of order 1. As you see in this case, if you do partially differentiate with respect to x, a is a, plug in this value over here, so you have partial differential equation. But if you partially differentiate with respect to y, there is another expression for a, so you get another partial differential equation. So in this case, we have two possibilities of partial differential equation. Third possibility, if the number of arbitrary constants are greater than, if the number of arbitrary constants greater than the number of independent variables, so then the ordinary differential equation is generally going to be of higher order than the first order. Like in this case, we have three arbitrary constants a, b, c, two independent variables, and eventually by doing all this hard working, we see one of the possibility of the partial differential equation, second possibility of the partial differential equation, and there is going to be another one. So these are three second order partial differential equation. In case if the number of arbitrary constants is going to be greater, this number is greater than the number of independent variables. Now we move on. There is another chance of obtaining a partial differential equation or for formulating a partial differential equation by eliminating arbitrary functions. Previously, we have seen a few examples where we get rid of arbitrary constants. Now we are interested to eliminate arbitrary functions from the given relation. Like in this example, we have u as a function of y and x, f of y upon x, and we are interested to find the corresponding partial differential equation. In the second example, u is a function of x and t, but behind the scene we have two arbitrary functions, capital F and capital G. Take the first one. Now, if you partially differentiate u with respect to x and y respectively, we will be having, you see that, first of all, derivative to f, whatever it is, so it is f prime, and then further derivative to y upon x with respect to x, it will turn out to be minus y upon x square. So we take it outside this one or before f prime. And then once we differentiate partially with respect to y, so first of all, derivative to this expression, f prime, and then further derivative to this expression, so it will turn out to be 1 upon x. So 1 upon x times f prime of y upon x. So we have partial derivative of u with respect to x and y. Since we are interested to get rid of this arbitrary function f, it is a function of y and x. I mean, the expression would be in the fractional form y upon x everywhere, wherever the variable is involved. Just like f of x, x is there, f of y is there. So it is f of y upon x. Means everywhere, wherever the variable is involved in the term, it is going to be in that fractional form, y upon x, y upon x. So our target is to get rid of f. We need to eliminate it. So how do we eliminate? So you see that they are closely resembled with each other. Only difference is there if you do multiply equation number 20 by x, this 1x in the denominator is going to cancel out. And if you multiply 21 by y, so you see that the right hand side is going to be identical except the sign. They are going to be identical with different signs. So that's what we are interested for. We multiply equation number 20 by x, 21 by y, and then add together. So once we add, the right hand side is going to cancel out. So left hand side, x time partial u upon partial x plus y time partial u upon partial y equal to 0. So is going to be a partial differential equation for one. Secondly, if you look into the second part of this example, we have f and g, two arbitrary functions are there, and u is going to be function of x and t instead of x and y. So what we do, since we have two arbitrary functions, we will move on to second derivatives. Take partial derivatives of u with respect to x and t. So if you twice differentiate this equation number 23 partially with respect to x, so first order is there, second order is there, 24 is the second order equation because it does involve second derivative over there. So we are interested to keep an eye on this equation number 24. Similarly, twice differentiating equation number 23 partially with respect to t. So the first derivative with respect to t, simple is it. I mean, first of all, derivative to this one, and then with the extension, derivative to whatever inside the bracket. So minus t, minus c is there because t is going to be differentiated with respect to t, minus c. From here, it's plus c. Further, once more, if you differentiate this one, it is going to be second derivative, multiple of minus c. So minus c is going to be c square. One more c from here, along with g double prime. So this is how we will be having this one. Now, if you closely look into the expressions on the right hand side of 24 and 25, by taking c square common, so rest of the expression is identical to that one. Many ways you can play with. In other words, we could say that replace an expression for f double prime plus g double prime as partial to u upon partial x square. So in other words, we take the value as an expression from 24 and plug in over here in 25. Once we do that, it will turn out to be something like that. Rearranging the factors, we end up with partial 2u upon partial x square equal to 1 upon c square partial 2u upon partial t. So we write it down in that particular fashion because it is going to be very, very famous one-dimensional wave equation where we have vibrations over there, we have oscillations over there. So it is going to be mathematical modeling of wave one-dimensional. Why so? Because we have only one spatial component. Spatial means space coordinate. One x is there. It's a temporal time t. But because we have only one space component, spatial component is there. So this is how we say that it is going to be one-dimensional. Yes, you could have partial 2u upon partial x square plus partial 2u upon partial y square equal to the right-hand side. So it will turn out to be two-dimensional wave equation. And if you add one more, partial 2u upon partial g square, so it will turn out to be three-dimensional wave equation. I mean, this is how the wave is going to move. But anyway, in this example, we have obtained second-order partial differential equation, but we say that it is going to be one-dimensional. The above equation is called as one-dimensional wave equation describing the transverse vibrations of a stretched string. And if you are interested to see the solution of this equation, I mean that one, that's a second order, but one-dimensional, name as wave equation, one-dimensional wave equation. So the solution is going to be that one. So this is how we move in the reverse direction. Solution is there, we form a differential equation. Now, if you have a differential equation and simplify that one, eventually you will get down 23, equation number 23. So equation number 23 is the generalized form of the solution to this one-dimensional wave equation. So now we have seen quite a few examples. First three examples, eliminating arbitrary constants, and the last two examples by eliminating arbitrary functions. So from these examples, as illustrated above, it is very clear that a partial differential equation can be obtained by eliminating arbitrary constants or by eliminating arbitrary functions. Last two examples by eliminating arbitrary functions. Solution of the partial differential equations. Now we are interested to find solution. How do we find solution of partial differential equation? Different criterions are there. If you remember from the previous part, the ordinary differential equations, how many possibilities are there? Plenty, because of the type of the differential equation, whether it is variable separable, homogeneous, exact, non-exact, linear, Bernoulli, whatever it is. I mean, depends upon the type, depends upon the shape of the equation. So we have different criteria to obtain the solution of that particular type of the equation. So same is the case, we are expecting to have different criteria in accordance with different types, with different forms of the equations. So if partial differential equation involves derivatives with respect to one of the independent variables only, I mean, this is one of the criteria. We see that yes, the dependent variable has got more than one independent variables, but as a particular case, differential equation is there, but it involves derivatives with respect to one of the independent variables. Derivatives are there, but they are going to be only with respect to one independent variable. So we can solve it like an ordinary differential equation, treating all other independent variables as fixed parameters. They are going to be held fixed. So how do we look into the solution? For example, u is a function of x and y generally. I mean, up to this point, u is going to be a function of x, y. You see that we have a second partial derivative of u, but this is going to be with respect to x only. So fulfill this criterion. So we can solve it just like an ordinary differential equation by keeping all the other variables held fixed. So take this case, u is going to be dependent variable. It has second partial derivative with respect to x. So what we do, we need to look into the solution. It's a double rate of change of u with respect to x. So in order to kill the change in u, we need to integrate it, because integration is the reverse process. We differentiate, we get a change, and then we are interested to kill that change. How we do that? By integrating. Since the change is occurred with respect to x, we have to integrate with respect to x. So once we integrate with respect to x, you know that to the left hand side, one of the change is going to cancel out. Means one of the derivative is going to cancel out, and we left from second to first derivative. But to the right hand side, keep an eye. When we talk about pure ordinary differential equations, we involve constant, arbitrary constants. Whether the integration is performed with respect to x or y, whatever is the criterion is there, the constant of integration is going to be an arbitrary constant. Since we are integrating with respect to x and we have to help fix all the other variables, so in this case, the constant of integration is going to be function of the other independent variable y. So ux, there must be arbitrary constant, but in this case it is going to be arbitrary function f of y. Another way to cross check that, since we integrate 26 and we get that one, so surely if you differentiate this one once more partially with respect to it, you should get 26. So differentiating both sides partially with respect to x, what happened? To the left hand side, second derivative with respect to x. To the right hand side, it's independent of x, and the derivative with respect to x of a function which is independent of x is going to be 0. So this is how you will get 26. Yes, this is going to be double check or quantify the step that we have done. We integrate with respect to x and we involve an arbitrary function f of y. Once more, we need to integrate with respect to x. And once you integrate the right hand side, it's a function of y. So with respect to x, it is going to be x times f of y. And once more, you need to involve arbitrary function. So here you go. X times f of y plus another arbitrary function. And that arbitrary function is again going to be function of the variable y. To the left hand side, we left with u. Second derivative, first derivative, and eventually u. And since u is going to be function of xy, so you can write it down, u of xy. So this is all. We had second order partial differential equation, and how do we get down with the solution? Twice integrating with respect to x. Now, if you look into the second part, u, y means it's partial derivative of u with respect to y. U is going to be function of the variable x and y. So how do we handle this one? Since now we have entirely different criteria because of the situation is there. Not only the partial derivative of u is there, but also the derivative is there. So the given equation could also be written as, and that's it. I normally sneeze 3 times. Alhamdulillah, alhamdulillah. Okay, So u, partial derivative of u with respect to y is there, and it can be rearranged in that particular fashion. To the left-hand side, we have u and its partial derivative with respect to y. So what we do, we integrate both sides with respect to y. No, fundamental criterion is there. Function is there and its derivative is there, just like 1 upon x. X is in the denominator and its derivative 1 is available in the numerator. So what we do, we look into the formulation. It will take us to natural log of that denominator. So u is there and its partial derivative with respect to y is there, and we are integrating with respect to y. So it is going to be natural log of u. To the right hand side, we have to integrate with respect to y. So we'll cancel out, and plus the constant of integration. And again, remember, the constant of integration is going to be function of the other variable. Since we are integrating with respect to y, so the arbitrary function will be function of variable x. Generally, to make things simple, we do involve natural log. There is no harm doing that. To make things simple, so we can also take arbitrary constant, arbitrary function in terms of natural log. Taking antilog on both sides, we eventually are having this expression, u of xy equal to f of x times e raised to power x y squared. So this is all. We will find the solution based upon different scenario, based upon different configuration. We find the corresponding solution of partial differential equations. Take another example. Solve the following second order partial differential equation. Now you see that not only the second derivative, first derivative, but also the dependent variable is there. So if you assume partial derivative, that symbolic representation by capital D as a D operator, then the second partial derivative symbolic representation is going to be replaced by D square. So if you do that to the left hand side, you see that eventually it will turn out to be D square plus 3D minus 4 times U is equal to 12, just like an ordinary differential equation. So we can apply the undetermined coefficient method to find the solution. Before we move on, we have to find the corresponding auxiliary equation corresponding to f of d. F of d is equal to d square plus 3d minus 4. Only thing that you need to keep an eye, you have to introduce those arbitrary constants by arbitrary functions. Remember, in the case of higher order ordinary differential equation, we do write it down. For example, if m1, m2 are going to be the roots of the auxiliary equation, how do we write it down the solution? C1 e raised to power m1x plus C2 e raised to power m2x. Now C1 and C2 are going to be replaced by functions of the variable y, because we have derivative of u with respect to x. So you can write it down, f of y times e raised to power m1x, y1 is to be obtained from here, plus g of y times e raised to power m2x. So this is all. You will write down the solution. You try yourself. In the meanwhile, I generate a poll for attendance purpose. So today is 24th of July 2020, and we are interested to see all present. The attendance of 24th of July 2020. So here you go. So poll has been created. Mark your attendance over there appropriately. And you try to find the corresponding auxiliary equation corresponding to f of d. F of m would be m square plus 3m minus 4 to get the corresponding values of m. So you will be having two roots.
Sir, your screen is stuck. You can only see the example of d square plus 3d minus 4 times u equals 12.
Sorry, hang on. Who is it? So, yep. What's your question, please?
Sir, I was asking that your slide was stuck. We can't see the questions you are talking about.
So can you see now?
No, you haven't shared the screen.
It's there. It's there. Screen is shared. I believe that you should be able to see that. Is it visible to all the other people, please?
Is being shared. Only your desktop screen is being shared, not the slides.
No, it's there. Anyway, I do it again. Is it visible, this slide, the presentation now? This slide?
Yes, sir. But
Yes, that's what you have to do.
please go to the next slide.
I know it's there. With different topic, you have to complete it yourself. I gave you idea how we do that. It's assumed knowledge. We have gone through with that many times, I believe. It's a second order differential equation. Since the derivatives involved are with respect to only one independent variable, so you can treat them just like the ordinary differential equation. So pretty much on the same line, you see that it's f of d y is equal to 12, for example. So f of d is equal to this one. From there, you find the corresponding auxiliary equation f of m, put it equal to 0, get the corresponding values of m. Based upon the nature of the roots, you will have to find the solution that is going to be complementary solution, complementary function u c as a subscript of xy would be equal to, write it down the solution, and then you need to find the particular solution by applying the method of undetermined coefficients, one of the viable option, because the right hand side is a constant. You can take an expression from the table of undetermined coefficients and then apply that method to get down with the solution. So this is how you will have to find UC, complementary function, and then UP, particular integral. The combination of UC and UP will take you to the general solution of the given, in this case, partial differential equation. But we do simplify just like the ordinary differential equation. So that's the idea I gave you. You have to do it yourself, try yourself. That's what we are talking about. Is that clear now? Does it make sense? All the undetermined constants are in terms of x. No, it's a constant value, constant value. You need to find the constant, arbitrary constant. So look into the table of undetermined coefficients method. If there is a constant, a, small a, what will be the expression from the table for yp? So over here, it is going to be up. So take that expression, then simplify just like the ordinary differential equation of higher order.